Hello, everybody. We're just going to wait a couple more minutes for any last minute joiners, and then we'll go ahead and get started. Oh, hello, Anu. How are you doing?
Great to see so many people jumping in on the chat line.
Hello, Greece. Hello, Turkey. We're here. I'm here in New York, and Brad is in Australia.
That's it. It's amazing. It sounds like we have a really good distribution of people from everywhere across the world.
Hello, Mexico. Hi, Egypt. Hello, Puerto Rico. Hello, India. We are everywhere. Thank you, everybody. Yes. Hello, Buffalo. Hello, Peru and Washington. Oh, what a great group. Thank you, everybody, for coming and joining us from, everywhere. That's so wonderful. Okay, well, we've given it a few minutes, so we'll go ahead and get started now. I guess any latecomers aren't going to get shout-outs to their country. So sad. Hello, and welcome to Strayos' webinar, Finding the Seam, Auto-Detect Geology with Drones to Optimize Your Blast. My name is Kimberly Sahu. I'm General Manager at Strayos. Presenting today, we have Brad Gyngell, Blasting Optimization Expert. Brad spent the first phase of his career helping over 100 sites optimize drill and blast activities as a mining engineer with the world's leading explosives providers, Orica and Dyno Nobel. He then expanded the scope of his support to encompass all commercial operational functions by moving into management consulting with the top-tier firm, Boston Consulting Group. Brad holds a Bachelor's of Engineering in Mining Engineering from UNSW and an MBA in Finance and Entrepreneurship from Carnegie Mellon University. A couple quick notes before we get started. Please make sure to put your questions in the questions section rather than the chat box. That way we can make sure that we address everybody and no questions get lost in the shuffle. We will be sending out a link with the recording of the webinar after the webinar has finished, so keep an eye on your email. If you would like a certificate of completion, please email us at hello@strayos.com. We will also be emailing answers to all the questions that are asked during this webinar within a couple days, so don't be shy about asking questions. And without further ado, Brad Gyngell.
Thanks, Kim. And thank you everyone here for joining us today. As Kim said, I'm Brad, and I'm super excited to share some of my perspectives with you on the emerging technologies shaping the way that we bring geotechnical information into blasting. So let's kick off. All right, so what are we going to go through today? We're going to first talk about, we're going to do a quick overview of Strayos. Who are we? Why are we talking to you about this topic? But then we're going to jump straight into some really tangible, actionable workflows and techniques for helping you incorporate geotechnical information into your blasting. So we'll kind of talk about what is RockMass AI and why is it important? What's the value? What are the use cases? And then we'll go into a little bit on best practice data collection techniques for using drones. And then we'll walk through 3 specific use cases, how you can apply this in coal, quarries, and metals. And finally, we'll wrap up with a little bit of a Q&A. So does that sound good to everyone? I will kick us off. Awesome. So who is Strayos? So for those of you who don't know us, Strayos is basically, we're a software company. We build software. We let mines, quarries plan and optimize operations. So it's basically one single platform where you can process data from drones, smart drills, kind of traditional sources of data, plus these new sources of data. You can automatically extract the information that matters using artificial intelligence. So that's using computer vision to detect things on photo models. That's also analyzing trends in kind of data from OEM equipment, etc. And then once you have that, all of that information, we allow you to design, optimize, and report all from the same platform, all basically from either the browser in the cloud or on your own device standalone. So, next slide. Where are we? So Strayos has been around since 2016, about 5 years ago, and we're already used across about 600 sites across 8 countries all around the world. So it's great that we have people here from all around the world. It's amazing. We're also used all around the world. We have a very global footprint and very global customer support presence as well. We have people in the US, Europe, Asia, and Australia. So what does Strayos actually provide? More specifically, it's along each step of the mining value chain, AI tools that assist with that kind of design and optimization. So at the beginning, we have tools that can assist with mine planning and surveying, so building models, working out volumes for the different blocks, etc. We have geology analysis, which is really the big focus of today, is this auto detection of geological features. In terms of drilling, we have measure while drilling integration. So you can basically receive and pull data directly to and from smart drills. We have blasting design and also prediction tools. So that's, we allow you to actually do a drill pattern design, for example, on the model that you've created, and then predict what those blast outcomes are going to look like from that. Load and haul, then we have some analytics where basically we can auto detect all the haul roads and then check them for things like, is the grade too steep here? Is the berm height too low there, etc. And to assist that kind of the processing step, we have AI that can detect fragmentation of your muck pile to basically allow you to dial in how your blasting parameters to optimize for the mill. And then finally, we have on the reporting side, we have a lot of different things, but I guess on the example here is stockpile reporting. So automated detection of stockpiles, and then that kind of continual update of the volumes in those stockpiles at whatever frequency you'd like to fly and update them. Awesome. So I'll move on to kind of what's an example workflow that you might see when you're using Strayos. So to kind of make this a bit more real, what you might do as a user is fly a drone along a bench, capture a whole bunch of pictures. This could just be, an off-the-shelf drone for $1,000 or whatever. You'll upload those pictures to our cloud platform, or we also have an offline version as well, because we know a lot of people operate in areas with low connectivity. We'll process everything on our end, and then basically just give it back to you to do the design and optimization with tools that we have built in, and then you print off the report. And in this case, the example is a burden report with some measure while drilling data in there to basically take back out in the field and use in your operations. So that is the quick Strayos overview. I'm keen now to get everyone here involved. So I'm, not the only one doing any work around here, and I'll open up the first poll just to see how many of you are using drones at the moment. So hopefully you can see this on your screen now. Yep, okay, I see some answers coming in. How often do you use drones for work? Yeah, wow, it's interesting. I can see it's kind of a bit of a very split field. People either using drones all the time or never. We have a few more rarelies though coming in now. Good to see. Okay, I think we've kind of stabilized the numbers. Okay, so it's interesting. It sounds like we have quite a few kind of heavy drone users, and then some people who never use them. So that's going to be interesting going forward. I'll close the poll down now and then move on. So yeah, that's cool because yeah, for those of you who don't use drones, will have a bit of information on the potential that they can provide, and those of you who do will have a bit of information on the kind of best practices for using them. So hopefully we have something for everybody. So let's move on. Here's kind of getting into the main body of the talk for today, about what is rock mass AI and why is it important. So new sensor technologies have basically enabled us to collect all these new types of rich data that we couldn't collect before. And those are coming from various sources. They can come from drones, they can come from satellites, come from cameras. There's a lot of, I guess there's a lot more as well that I haven't included. Smart drills, measure while drilling data is another example. But basically there are a lot of, I guess when we're talking about visual data, there's basically a whole new world out there now of opportunity where we can get cameras to places that we couldn't get them before, and we can get new types of sensors involved that we didn't have before. And we also have the AI to actually interpret some of that information. So how do we get these new forms of data? Well, this is the kind of tip for best practice flight techniques. If you're using a drone, for example, and you're flying a bench, what we need people to do is basically get 70 to 80% overlap between the pictures. Our technique is kind of fly across the top and then step back, tilt the camera to about 40 to 50 degrees in that second picture so you can actually see the face as well. Scan along the face there, and then do some scanning along the floor surface as well. And yeah, it's really critical to get that middle section right. You really want to make sure that you get the oblique images, the ones where you've tilted the camera. You really want to make sure that you can get under any cracks or any overhangs in the face when you're flying, because if there's something that's not in the photo, then it's not going to be in the model. So once you have this data, the really exciting thing is that now we have AI that can process it. So it's not just the old taking photos in the field and then drawing some lines on in paint and handing it over to a blaster or a driller, or handing it over to geotech, for example. It's actually having this full 3D photo model that software can look over and automatically detect cracks in. The other thing is with hyperspectral imagery, it's also possible to basically see where different types of mineralization are, either in the face or in the muck pile. So there's a whole bunch of exciting new things we can do with this new data. And why is that even important? Because knowing where geological features are in blasting is definitely critical to designing a good blast. Basically, I've got 3 use cases here that we're going to walk through. The first one is around maximizing coal recovery. So basically knowing where the seam is at a very accurate height, or depth rather, so that you can get your standoff right and avoid any coal loss. Secondly, preventing fly rock. And so this is what I'm going to talk to in terms of quarries, but it still applies everywhere, is basically knowing the depth of where your cracks are, so that you can, especially if they're, large joint planes that are prone to kind of gas escaping, face ejection, things like that, and being able to stem through those joint planes, especially on your front row holes. And then finally is optimizing your milling performance. So basically being selective about where you throw different parts of the blast to try and separate basically good material from bad material, or ore zones of different types. Doing that in the blasting stage, and then also in the digging stage. So if you fly your muck pile, being able to see different ore zones, basically. So, all right, now that we've gone over why it's important, what these kind of use cases are, I'll jump into a new poll because I'm keen to see, so what types of mining does everyone work in here? I know that a lot of people probably could tick multiple boxes for this one. Unfortunately, Webinar Ninja didn't want to let us do that. So we want to see where are most people from today. It'll help me understand where I should spend most of my time. And it's good. Looks like we do have people from everywhere, which is great. Definitely a heavy quarry focus, bit of metals, bit of coal. So this is good to see. It's actually evening up a bit more now. The quarry people were just the fastest. Okay, great. I might leave it there because I think we've kind of got the gist of it. Awesome. So let's get into real world use cases for this stuff. So seeing as we had a kind of a small percentage of people who primarily work in coal, do basically a quick background on cast blasting in coal. Basically, the idea is to leave a standoff above the coal, basically a buffer zone, so that you avoid pulverizing it. If you put explosives too close to the coal, you'll end up destroying coal and destroying a lot of value in the process. What that kind of looks like is, you see here, this is a picture that gets used around the internet a lot, where kind of you have these big trenches above which were rows of holes that were drilled too close, and it ended up destroying a lot of coal. And so the kind of the normal ways of dealing with this are you use touch coal holes. Touch coal data is probably the most common way, where basically you drill every 5th hole down to the coal to work out where the coal seam is. The problem is, and this is a case that I've had a few times, so definitely keen to hear in the chat if anyone else has cases like this, where your touch coal holes don't give you an accurate picture of where the seam is. So you might have a seam that does something jagged like this. You have some big discontinuity, and if you create a surface purely from the touch coal holes, it would look like that green line there. And if you then design your drill holes to that depth, you'll end up being too close to the coal in the middle, and probably too far from the coal over on the right-hand side there. And yeah, this is an issue that I've seen quite a few sites. You have the solution is often people going out and trying to take photos in the face and then try and match that up with where different holes are, but you still don't have an accurate view of the depths, and it's a very difficult place to be, and you end up having to do things like either drilling more touch coal holes and backfilling more, or gamma logging, and yeah, you get yourself into a lot of wasted time and effort. And this is where kind of detailed those things down. So yeah, your options are at the moment, your regular touch coal strategy of just drilling every 5th hole to touch coal. But as you saw in that last picture, you might not get the discontinuities. Drilling every hole you could do, but then you would have to backfill every hole, which is not ideal. It can take a lot of time. Gamma logging is very accurate. Again, you'd have to drill through every hole and backfill it. It's probably more useful for kind of through seam applications. Manual photo comparisons, as I mentioned, you don't know the depth. So the solution is that now with kind of AI, what you could do is you can fly over the bench, capture those the drone data. So basically get all those pictures, upload them into a platform to process that data. You can then basically see all of that. You have like a 3D photo model of the bench, also with all that geotechnical information highlighted already. And you can bring that into your blast design software, and then you can design the drill holes based on that seam depth. So you can basically project that seam depth back to your holes, design them. Then when you actually go to drill the holes, and once you've been drilling, you can add that touch coal data in to generate an even more accurate coal surface, basically. And then you can use that to backfill the holes off and make sure that all your holes are standing off coal. Finally, the other bonus is that once you have that much more accurate seam surface in there, you have a baseline for measuring coal loss, because it's super important to avoid the coal loss, but you also need to be able to measure what you're doing. You need to be able to know how much coal you are actually losing, because maybe you're losing it from another source, not just the lack of standoff. So very important to have an accurate view of the seam. Awesome. So I'll kind of pause for a second. So that was the coal use case. The next thing that I'm going to talk about is the quarrying use case. And this is where we had kind of probably half the people joining from. So I'll spend a bit of time on it, and yeah, feel free to throw your questions into the questions area if you have any. The main use case for quarries that I see is basically allowing you to stem through joints. You have cases where you'll have a plane, especially on some sites. You'll know that there's a plane there that is just prone to ejection, and some sites will already know and have methods for trying to stem through that. And some sites, it might be more variable. You might miss things, and you might end up just having a site where you hopefully is further from houses and from anything else, where you just end up having a lot more ejection incidents and gas escape incidents. And Strayos and this kind of rock mass AI crack detection can definitely help in both of these situations. So the quick 101 for what I'm talking about is in this diagram here, in my very rough bench diagram on the right, you see if you basically have a joint plane, you know where it is, you can adjust loading in those holes to put stemming through that section. And that prevents then when you blast those gases from escaping out the face. And it also stops kind of hole-to-hole interaction. So you might have in the same types of situations, one hole at the start of the shot at the front, detonating and then desensitizing holes further back in the shot. If you don't have adequate burning front, this could even kind of cut off boosters, which could leave you with misfires. But in any case, it could desensitize the bulk explosive, and that could give you kind of much worse blasting outcomes. So there's a lot of reasons why this is an important thing to do to stem through those joint planes. And so the traditional methods, which everyone's probably kind of aware of, one, you could use the burden pole, push it out over the face, measuring tape, have someone down below looking and saying, yep, this is where you're at, this is how your plumb bob is at the crack, and then at the top you measure, here's my depth of that crack, bring that back to the hole, and then you kind of where you're at. That's one way of dealing with it. The kind of issues with that is that it's a kind of a slow manual process. It takes multiple people, and you have to do it for every single hole. You've also got people in kind of potentially dangerous situations, standing too close to the crest or standing underneath the high wall. And lastly, it's still subjective. You're still relying on a person at the bottom to kind of tell you when it's at the right height. So there is it's not a perfect solution. And with lasers on the right-hand side, if you are shooting in kind of a seam, and with a 2D laser, you'd still need two people, someone at the top over the hole, who's basically holding up the reflector, and then basically allowing you to calibrate how deep that crack is. Still a manual process with multiple people involved. It's an extra step that you have to take on site. That's time that you could spend loading, basically. Then it's time that you could spend laying out, designing your blast. Then the other option is 3D laser, kind of shooting in the crack when you do your design. That's a slightly faster, but you're still kind of manually shooting it in. You have to know where it is. You have to be able to look through that site and pick it up. Which, if you have one crack that could be that's very obvious, then it can work, but it's still subjective. And if you have multiple cracks, then that can be more difficult. Also, it gets very difficult if you have a corner and you have to shoot kind of around a corner. So that's kind of like what you can do with traditional methods, and why those can be challenging, time-consuming, kind of less safe in some circumstances. So the workflow that that you can kind of now do using drones and AI is to fly your drone, capture all of the data, same as last time, upload it to be processed. You have your 3D kind of model of the face. What you'll basically immediately get this view of where all of those cracks are along the face, around any corners, and you'll be able to optionally, if you have a smart drill, import measure while drilling data on top of that. What that will allow you then to do is basically marry up your measure while drilling data with your kind of crack detection data from the face, so that you can kind of pick up key signatures in the measure while drilling data that kind of give away when when they're intersecting that crack, and that can then allow you to not just know on the face where that crack is, but get a view of what that plane is doing throughout the body of your shot. So that's a really good one for kind of creating a really holistic kind of mapping of planes subsurface in your shots. What you can then do is basically produce reports that can show that per hole. So you'll be in the field when you're loading, and you'll know this is my hole number 6, and at depth of I'm going to use meters because it seems like we've got people from all over the world. Depth of 5 meters, say. I've got on my face hole, I can see there's a crack here, lines up with a few red lines in my in my measure while drilling data. So I'm pretty sure that this is the zone I should stem through. Probably stem through an extra half meter on either side of that as well, to make sure that I've really nailed it and really avoided that joint plane. And I can even see, I can print that out. So in the field, I know that that's where that zone is. And then I can even see for the holes behind that as well, that's where I need to stem through. Maybe it's at 7 meters behind, because I saw my crack on the face was at 5 meters, picked up the measure while drilling data at 6 meters. So I know the one behind it has that joint plane at roughly 7 meters of depth. So that's kind of the cool new opportunities for using this in the quarry use cases. Basically giving you more safety, because you know where your cracks are, you know where your joint planes are, and also more safety in the process for finding them. You don't have to climb around high walls, and you also get to speed up the process. Basically, you basically just fly it, and then you get the results right there in front of you, that you can then just export and bring out in the field. And lastly, your performance should improve, because, as you said at the beginning, you won't have as many issues losing energy out the face or potentially desensitizing other columns in the blast behind you. Cool. So that's our quarry use case. I will now move on to a kind of a metals use case, but this one still can apply to quarries in certain circumstances as well. So hopefully this is another one that's kind of interesting for everybody, even coal potentially. So this is more of a, this one's a little bit different, because in the last 2 use cases, we've been mostly talking about visual data in the kind of red, green, blue spectrum. But now I'm going to go talk about hyperspectral data a bit more. So firstly, what is hyperspectral imaging? Hyperspectral imaging is basically cameras that can capture wavelengths outside of that red, green, blue kind of visible spectrum of light. It's useful because different minerals can kind of reflect different, have different signatures basically for reflecting different types of light, different frequencies of light. And using AI, you can process these and use that to kind of pick out, hey, this is, here I'm seeing a lot of the signature for this type of mineral, and here I'm seeing this signature for this different type of mineral. So that AI can kind of work all that out, and the result is that you can get a map that then shows you this is where you have all of these different types of minerals around a site, around a bench, around a muck pile, or even at a higher level around a whole state or something, if you're kind of looking for ways to speed up the exploration process. So the use case that I'm going to introduce for metals is basically separating ore zones using timing in blasting. So a key outcome for metals mines that they're trying to achieve often is to separate different types of ore. So either ore from waste, or an ore with a certain type of mineral from an ore with a different type of mineral. And that really facilitates a lot more of a efficient milling process, basically. So it offers the opportunity to really improve the kind of throughput that you get, reduce the amount of waste as well. So the way to do this ideally is at the blasting phase, stop everything getting mixed up in the first place. If you know that this half of the bench, for example, is high grade and this half of the bench is low grade, time the shot such that you'd probably initiate from the bottom right and the bottom left, and then pull each of those sections apart from each other. The challenge is, I guess, see those middle holes there. They're pretty close to that boundary. So you don't know, if you don't have accurate view of kind of where high grade and where low grade is, you might be pulling certain holes in the wrong direction. And that's really what the challenge of this is that the way that it's worked out today, using kind of assay holes, geologists going and working out, okay, here's my doing some basic sampling testing on the bench before you blast, to work out where they think or where they find different grades of ore, for example, and then interpolating between those points. You don't get a very high resolution picture. You just get kind of low resolution picture with interpolations between. And those assumptions, can be right, but they also might not be. You might have high grade kind of only go right up to just past those top holes, and then suddenly it switches to low grade, but you won't know that. Hyperspectral imagery is now, and this is kind of the exciting kind of front of new research, is that kind of hyperspectral imagery has been shown now to be able to detect different kind of ore grades in the bench. So that's kind of using a camera. You could point it at the bench and actually detect, here is exactly where my high grade stops and here's where my low grade starts. So the example workflow for using this would be still capture those assay holes in the first place, the data from those assay holes, because you need to calibrate that hyperspectral model. You'd still capture the kind of the 3D visual model and the hyperspectral model for the bench. You could bring all of that together, and then you'd have and kind of have this very accurate kind of defined view of where your different ore zones are. and you could then use that to adjust your timing to pull different parts of the shot in different directions. So that's how you can use this to really increase your or decrease your dilution rather, making sure that you're separating different types of ore from one another at the very beginning before they get mixed together. The other application that you can use in metals or even in quarries for this is that you can detect pretty easily signatures for kind of waste materials like clay and things like that in the muck pile. So after you've blasted, you could then fly the drone with a hyperspectral camera, for example, over the muck pile. You could figure out this half of my muck pile is actually full of kind of waste material, impurities, and you could then get that, tell the loader operator basically to put that into a different area to the rest of your ore, and that could really kind of optimize how your plant runs, how your plant processes all of that material. So that's another really powerful use case for how basically this hyperspectral imagery plus AI plus drones can really help in quarries and help improve your plant performance. Nice. So those are the use cases for today. I'm keen now to get everyone's feedback really on, from all these use cases, what are the ones that they feel that they're most interested to learn about more. So I know we had a lot of quarry people in here, but that doesn't mean you'll have to pick the fly rock one. Yeah, I'm keen to know, you know, if we produce kind of more content, what should we angle it towards? Is it that, you know, kind of ensuring standoff, reducing or maximizing the recovery, preventing fly rock, the hyperspectral kind of stuff in the bench before the blast, or hyperspectral in the muck pile to assist loading after the blast? So really interesting results here. I can see we got definitely, you know, a lot of people that do that are interested in the fly rock side of things, but the strongest one is actually the hyperspectral use case for ore zones in bench, which is cool. So I'm not surprised. It's also the most recent one in everyone's memory, so maybe that's it. Cool. Okay, that's really useful to know. So yeah, as Kim said at the beginning, we're kind of answering everything after. We'll make sure that we kind of follow through with some more material after this, and this will be good for helping us know, you know, where we need to add more detail. And I'll jump into Q&A, and I'll preface this by saying I'm a blasting engineer by background. So if some things are more technical than I know about, then I might say that I have to come back to you later. What type of case studies did your team complete to verify joint ID? What kind of MWD properties do you focus on? So case studies to verify the joint ID. Type of case studies, I guess, is these were in quarries. These have been kind of done in partnership with other with customers of ours who are actually doing it themselves in the field and using them. So the case studies have kind of been like joint projects with customers and with users. So those people kind of know their sites, know the joints already, and are kind of using Strayos to pick up those joints and then verify that those are the right ones. In terms of matching it with Mwd data, this is something where we'd be focusing, I guess, on your kind of pressure. Basically, yeah, all of your kind of most common MWD out of the box standard sensor metrics. We wouldn't be kind of creating any custom ones at this point based on a lot of the deeper machine data or anything like that. And yeah, I can definitely provide everyone more information on with like a sample report on what are the ones that we actually show on our default reports. All right, and next, have you explored many use cases, opportunities with hyperspectral cameras in quarries? Yes, that's a really interesting one. So no, not yet. So this is based on kind of, I put this presentation together based on not only what we've done, but some kind of emerging technologies that have the potential to kind of change how we do things, based on some research that I've been doing in the industry. And so, yeah, we haven't, I haven't personally done that, used the hyperspectral for different rock competencies or rock properties yet, but that's a super exciting use case that I'd love to test. So if you have, anyone that's out there that has some of these use cases that they want to test with us, reach out, and we're always keen to do that, basically. I guess what we have done is flown quarries to detect different mineralizations, which can sometimes be associated with different rock competencies. And I know that other people have flown to detect, you might, if you can pick up a clay signature really easily, maybe you'll know that that's a less competent material type, for example. Awesome. How does the Strayos platform integrate and exchange data with other systems on site, including mine planning systems, etc.? So yeah, that's a really good question. We've definitely built this with the goal of integrating seamlessly with as many things as we can, where we're trying to kind of look at this from a user workflow perspective and automate as many of the annoying redundant steps as possible. So in terms of how we integrate, for example, with OEM data, so for smart drills, you can use a thumb drive and literally from Strayos export the drill pattern, plug it into the smart drill and go. It'll work in that it's already in the right format. You can then bring the MWD data straight back off the thumb drive, plug it into the computer, upload that to Strayos, and it'll work. And we also have integration over wireless enabled. So you can actually, without the thumb drive at all, if you have your smart drills connected to a wireless network or connected to the cellular network, you can, from the Strayos platform, just click a button and it can immediately appear at the drill. So that's a really exciting one. And then that also gives the opportunity for the drill, as it's drilling, to kind of have an almost real-time stream of data flowing back into the Strayos platform. So in terms of how it integrates with OEM systems, then that's how it could do that. In terms of how it integrates with other like mine planning software, we have a lot of different export types that we can kind of file types that we can produce for all this data. You can export in your kind of traditional DXF type forms, point clouds. Also kind of you can export the textures in kind of those 3D textured mesh formats as well. So really anything that you need, we can just export it and import it into your mine planning system. And likewise, the other direction, you can just export DXFs, etc., from mine planning and import them straight into Strayos. So that's an area where we've tried to make things as easy as possible. Let me go through. Oh, where's the next one? I saw one just there a second ago and then it's disappeared. Oh no, we just had another one pop up instead. Hyperspectral image, collect this individual photos or merge together, similar to photogrammetry. I think it depends. If it's a satellite picture, then it's probably already merged together. If it's the drone pictures, you'd still need to stitch them together. It might not be using the exact same kind of 3D module that we'd use for the visual ones, but the photos would still need to be stitched together and then turn into a texture to overlay over the map. Any thoughts on underground mining? We have we've definitely started to explore use cases in this area. For the moment, the focus of this was more on the open cut examples, but there's no reason that the hyperspectral stuff, for example, using there are ground-based cameras as well for that. There's no reason that all of those use cases couldn't also apply in the underground setting. In your experience, how much more exact RTK, PPK pictures and GCPs? So yeah, obviously when you capture your data, it's important if you're designing a blast to have everything accurate. The easiest way to put it is that without kind of survey control, you can still get a very accurate model. It just might all be shifted in space a little bit. So the whole thing generally just in the up down kind of Z direction. So if you try to compare it to if you try to export it, import it into your mine plan, the whole thing will still be in proportion to itself, but it might be a little bit higher or lower. That's generally the only issue. Without not using them, but anything that you do, any measurements that you do, burdens, anything like that within the model are still all accurate. The RTK and PPK though, definitely great ways if you want to build up that map over time and have everything kind of in the right place. Those definitely are kind of necessary when you're doing that kind of workflow. I'll maybe answer one more and then leave it because we're at almost 55 minutes now, but I keep seeing more questions coming in, wanting to jump on them. Water levels in different holes and design charging accordingly. That's not a use case that we've explored with it yet, but thinking about it, for holes that are potentially full of water versus not full of, versus have no water, I wouldn't be surprised if there was a way to tell. Picking that exact depth, I'm not sure about that that yet. Haven't tried that one, but that's a cool use case. If yeah, we kind of get a few more people asking for that, or if anyone wants to kind of explore an opportunity to partner and figure out if we can do that, then that's something that we're definitely always keen to do. So yeah, thanks guys. I will I'll leave it there to let everyone get out of here. But yeah, no, thanks for all the great questions. Super kind of diverse set as well across the kind of blasting stuff and the survey stuff and the technical software stuff. So good to see that everyone is super engaged. Yeah, I just wanted to wrap up by saying thanks for coming again. I hope this has given everyone a really good idea of kind of some of the emerging ways that we can use drones and AI to automatically detect geotechnical features to basically improve blasting outcomes. So for any further questions and for any more information on Strayos or just blasting in general in these kind of situations, always feel free to reach out to Strayos, reach out to me directly. My email is on the screen, brad.gyngell@strayos.com. And yeah, please join us in the future. We're going to be doing more of these webinars, trying to do one every month or so. So hope to see you all again next time. Thank you so much.